Check. Sound in the live stream. Sound. Yes. All right. Thanks. Sorry, guys. Good morning, everybody. Running around a little bit. Apologize. We're going to start, though, with a little warm-up music. In your Zoom, you probably noticed that you're not in Zoom rooms this morning. You're all in one giant group. Andrew's got a YouTube queued up, and he's going to start that playing for us. Somebody turn their, oh, you got your headphones on, so we won't be able to hear it. Turn your volume up. Are you in the Zoom? Okay. All right, go ahead and start that playing. Let's listen to the song for a minute. I'm gonna look for another slide here. Give me 1 second. Oh, crank it, Lillian. That's all you can do? Yeah. Oh, goodness. Where's the darn eye clicker now? Oh, for goodness sakes. What's going on? All right. Am I back? All right, guys. So, oh, iClicker's driving me crazy. It's stuck right here. Oh, I think I know what's happening. I'll fix it in a second. So a little train this morning of stage turning music, as we call it. When we meet in Pimentel Hall. Many of you haven't seen Pimentel Hall yet. It's ginormous. It has a 3-part stage that rotates. So 500 people can sit, and the chemistry instructor can be giving lecture on the other 2 parts of the stage. Other people can be preparing, and then we just rotate the stage in. So you bring the instructor in the stage to the students. It's pretty spectacular, and I have music playing when I usually start class because, and we call it stage turning music. While the stage turns, it goes. This train song has some special meaning for us. I said last time about the exam, it's not you, but it's me. And of course, this song is about a breakup where that line is right in there. You said it's not you, it's me. But it's also it's a song about a breakup, and the guy doesn't want to admit the breakup, or so when his friends ask, he just said she died. It's coming up with 50 ways to say that. The other thing about this song, and this is true of a lot of songs, the lyrics come hot and fast. And you know this with songs all the time. You love the song, you like the beat, and you'd love to sing along, but it just goes too fast. Do you feel like that in Chem 1 sometimes? I love the song, I like the beat, but it's going way too fast. I can't keep up. The lyrics are hilarious. You can't even hear them. Sometimes they go by so fast. But when your friends ask where you are, I'm going to say she went down in an airplane, fried getting suntan, fell in a cement mixer full of quicksand. That one's hard to catch. My favorite one, though, is she was caught in a mudslide, eaten by a lion, got run over by a crappy purple scion. That might be the best lyric in music history. Got run over by a crappy purple scion. So anyway, it's not you, it's me. You guys stay with us. I'm sure some of you are considering dropping the class. And then people would have said to you, weren't you taking Chem 1A this summer? What happened? And you'd go, it died. The whole thing died. Crappy purple scion. So take heart. Stay with you. We'll put the lyrics on the board, and we'll all get through Chem 1. So how many people do we have? Let's do one slide, and then we'll do the Zoom quiz so we get as many people here as possible. Okay, so we have that midterm bonus quiz coming up, and we'll do that. I'll go through one slide here, give everybody a chance. We also have the music. Oh, we have the music, so we're in. Let's just do that. So we have one of the most missed questions on the midterm, and you guys get a chance to do it again here. We'll use your iClicker, respond with your iClicker. If you get it right, you get a point. If you got it wrong on the exam, you get that point back. If you got it right on the exam, you get an extra point. Andrew, could we go back to Zoom rooms? So you'll be back in your Zoom rooms. It's open discussion. Talk about it amongst yourselves. In fact, you'll need some physical constants and stuff maybe to do that. Go ahead and just Google those. Get the equation sheet in front of you. You know you can go to the B Courses homepage and click on equation sheet right next to the midterm. Get what you need in front of you, and we'll just take a few minutes and go through it. Talk about it amongst yourselves. Make sure that you get it in your groups, and then respond. So that question is this one. Consider the equilibrium, the endothermic reaction below at equilibrium at 298, and the equilibrium partial pressures are here, the half an atmosphere, 1.5 atmospheres, and 0.5 atmospheres. I hope I transcribed that right. The question we have for you is, given that, what's the value of the standard state free energy difference between products and reactants at equilibrium? So I will start this iClicker, and we might have to, after this, stop and restart the iClicker. In fact, it's a good idea because then there'll only be that one question in that session, and we can collect everybody a little easier. So go ahead and respond to this. And actually, I'll shut up in a minute. Not all of you may have seen this one. The questions are taken from a pool, but I think according to the statistics, a lot of you saw this one. If you didn't see it, you're seeing it for the first time, you still get the free point. So think about that for a minute, and you have time, don't rush. We'll give you a few minutes, and register your vote. Okay, about half of you have responded. Take another minute, 60 seconds, and respond. We're not going to cut you off too fast, so talk about it amongst yourselves. Okay, let's take 30 seconds and push a button if you haven't so far. We'll see what you're thinking. How many do you think we'll get? We'll get about 98 if everybody responds. Okay. Okay, we have about 90, okay, 96 of you. We think we might have as many as 100. Okay, I'll give you a countdown here. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. No more responses coming in. Let's see what you think. We are a little bit over the map. Hopefully you can see that. So not quite a majority for B. The other two popular answers, A and E. So let's go over this one. Make this go back away. And I can't move that right now. So what's going on here? So the when you see this degree sign, that means the free energy difference between the products in their standard states and the reactants in their standard states. So that difference sets the value of the equilibrium constant. Delta G standard, you can think of it as the equilibrium constant because it's just, you just have to do minus RT ln K to get the equilibrium constant. So the standard state free energy difference, and the standard state is all these guys at 1 atmosphere, everybody at 1 atmosphere, 1 atmosphere of that, 1 atmosphere of that, 1 atmosphere of that. That's the standard state free energy difference. That's not where it is, but this number is a constant. This is the one thing we say, okay, we'll refer everything to this. If you don't have that degree sign, then it's the free energy difference between the products and reactants. And on the exam, I tried to make it obvious. I put reaction down there, that's the real-time measure. That is the free energy difference when you have these exact partial pressures. But if you have that degree sign, that means this partial pressure is 1, that partial pressure is 1, that partial pressure is 1, and you calculate a free energy difference by minus R, the temperature, and natural log of K. So how do you get to here then? Well, we said it's at equilibrium here. So these are the equilibrium pressures. So you can calculate K from the expression. K is products, the B pressure squared, the A pressure products over the reactants, the AB2 pressure squared. So you put in these equilibrium values, and that's going to give you the free energy difference and the standard state. So the standard state free energy difference defines K, or if you know K, you know the standard state free energy difference. So the answer here, I believe, was 2, minus 2. So that was the correct answer. I think those of you that were thinking 0 were thinking it's at equilibrium, so this is 0. If I have that, if that appears, that is a constant. Delta G standard, delta H standard, delta S standard. Those are constants. That's why we can plot them as slopes. Delta H standard slope of a ln k versus 1 over t. Those state variables with the standard sign are constants of the reaction. We know delta G, this one varies with temperature, but as long as you're at 1 temperature, you get 1 K, and we are at 1 temperature, so we get 1 equilibrium value of K. So that was the idea there. If you did do delta G of just the reaction, then yes, it's at equilibrium. So the free energy difference between the products and reactants now, under these conditions, half an atmosphere and 1.5 and 0.5, that is 0. But if they're all 1, the free energy difference is, all pressure is 1, the free energy difference is minus 2. And that tells you at equilibrium, it will favor, that's a negative number, it will favor the products. Okay. Good learning experience there. I think I'm just going to leave that darn thing. Hopefully this isn't too distracting. iClicker suddenly started doing this. It used to let me move that thing around, and it doesn't seem to do that anymore. So we talked yesterday about waves, and we talked about how if you have a oscillating charge that sent waves through space, if you get that oscillating charge or a rotating dipole with a high enough frequency, that caused the ether of space to ripple. That is, an electromagnetic wave radiates from that. It's an oscillating electric field. Perpendicular to it is an oscillating magnetic field. We're not as interested in that, but we understand there's this oscillating electric field. And it has that action at a distance. So we can demonstrate that. So let's do something complicated here. Let's pan back a little bit on the camera. Lillian, can you help for a second and just hold the other end of this cloth? Yeah, here, hold the other end of this cloth. I'm going to even flip the room lights on because they don't need to see the screen. So hold one end and go as far away from me as you can and hold it out. Oops, let's turn it over. And hold it out like this and hold both hands really tightly. Okay, so this represents the fabric, this weird fabric of space that ripples when I start a charge bouncing here. The bouncing of the charge ripples through space. I'll move. Ripples through space. And it travels at the speed of light. And so we know if we have a charge here close to me, that will go up and down when I go up and down. But the crazy thing is, if the charge is far from me, I can still influence it if I have that high frequency, high enough frequency to get that going. So it's like, this is my dog's ducky toy. So you can see I can influence it. And if I have a high amplitude wave, I can really get it going. Let's bring it in here a little bit more. If I have a high amplitude wave, that's this, I can really get it going. If I have a low amplitude wave, higher frequency, I can make it bounce around. So action at a distance because of this electromagnetic wave. Thank you, Lynn, that was wonderful. So these waves are blasting through space. Thanks for getting the camera shot back, Leo. So these waves radiate out through space. It just seems so dark. Radiate out through space, empty space. You don't need any medium to do it. And they follow this formula. Their wavelength and their frequency, the product of the wavelength and frequency is their speed, and their speed is fixed. All of them are traveling at the speed of light. And there's a huge spectrum. We're going to start using that word a lot. Spectrum, a spread of frequencies. And that spread of frequencies goes, and here I've written the wavelengths down here. The frequencies would be up here. So huge wavelengths from tiny wavelengths, 10 to the minus 16th meters, up to macroscopic wavelengths, kilometers long. So you have electromagnetic waves traveling through space. They're going at the speed of light, but their wavelength is macroscopic. It's kilometers long. Those are the radio waves that we talked about last time. The radio waves are hitting us right now. They're many meters, hundreds of meters long. They, your radio stations, they operate in, you turn on the radio to 95.3 megahertz. That's the frequency of the electromagnetic radiation. Its wavelength, you could calculate. If you know that frequency, you can calculate the wavelength, and you'll find it's in the range of meters long. So, but we also know that the energy in the wave goes as the frequency. And that actually, megahertz, is a relatively low frequency. It's 1,000,000 cycles per second, megahertz. Hertz is 1 over seconds. That sounds pretty fast, but it's very many. When you get the wavelength much shorter, that frequency goes way up. And that frequency means higher energy at this end. So higher energy down here, lower energy in the wave here, and that's why that's why the FCC, Federal Communications, FCC, the Federal Communications allows us to broadcast radio waves into the atmosphere. They're not going to hurt anybody. As you get to shorter wavelengths, so you'll recognize microwaves. These bands have names. Microwaves, they're slightly higher energy, and we use those. Those energies can get molecules moving. And that motion, as we know, translates into heat. We recognize that as an increase in temperature, more motion. We'll look at that a little more. As you get to even shorter frequencies, you get into this infrared IR band, and that is what we do kind of often refer to as heat, radiated heat in these frequency ranges. So now you start to feel it. You haven't felt the microwaves yet. Now you feel these. Beyond that, shorter than that, you have a tiny itty bitty little band right here in the middle that is, here we've written out wavelengths and amplitudes. So low wavelength, short wavelength, high frequency. Right here in the center, it's a tiny little band, just a few hundred nanometers long, from 400 to 700 nanometers in wavelength. Those electromagnetic waves stimulate our eyes. They stimulate the electrons, and we might look at that. They stimulate certain electronic transitions in molecules in our eyes. We see these. So we feel these, we see these, the visible spectrum. And on the visible spectrum, from 400 to 700 nanometers in wavelength, you should remember that. I'll give you wavelengths in this range all the time, and we'll assume you know they're visible ones. You don't have to know any other specific wavelengths. The visible range is something every biologist, every scientist should know anyway. You should know the visible range of electromagnetic radiation. It's important in almost all branches of science. If you go to shorter wavelength, even higher energy, and you have this feeling, you have some intuitive idea, ultraviolet radiation is higher energy. It's more dangerous than visible radiation. And that's because it's carrying even more energy. So now you're getting into the range where you can not just move the molecules, you can break them. And to go higher, X-rays, even shorter wavelengths, and gamma rays, very damaging radiation in that range. These are the radioactive decay, and gamma rays we know are very dangerous. They really are penetrating and can bust up molecules in our body. So that's the range of the electromagnetic spectrum. We're gonna talk about this all the time. This broad overview gives you an idea of how broad it is and how we name these bands. You've heard all the words before, so now you have them in an order, and you understand all of them are electromagnetic radiation. They're all traveling at the speed of light. It's the wavelength or the frequency that differentiates them. So there's another interesting property of this radiation. So if something is very hot, it's radiating heat, you can kind of see that. You see things that are red hot or white hot or yellow hot. You can look at the different colors of a flame and the intensity of radiation that's coming out to you. Your eyes are sensitive to some of it. Infrared's coming from this flame too. Your eyes aren't sensitive to that. But there are wavelengths coming from this heat source that your eyes are sensitive to. You see color in a flame. So why is that? Well, things that radiate have what we call perfect radiators. They radiate the entire spectrum. So if you're radiating this flame, you can imagine the entire spectrum of electromagnetic radiation coming out. And this is particularly true of the sun. From the sun, that whole frequency band, all those frequencies are being radiated at us. But it has an interesting property. So as you heat up this metal, it becomes red hot. If you continue to heat the metal, it continues to radiate and gets orange hot, and then it gets very much hotter and it gets white hot. And you can see that. And that's an interesting property of radiation. If something radiates perfectly, it radiates the entire spectrum, then the temperature of the radiation is reflected in the maximum of the radiation. So here's the whole spectrum of not the whole spectrum. Here's a spectrum of radiation. These are wavelengths. So along these wavelengths, there's an object radiating, and it's radiating along the whole spectrum, but it's not even. It doesn't radiate at every frequency or every wavelength evenly. There's peaks, and these peaks depend on the temperature. So if you have a radiator, so this metal, when it's white hot, is a radiator, and it's radiating the entire electromagnetic spectrum. If the temperature is high, this peak is in the visible range of wavelengths. So it radiates these the most. Could be radiating them all, but it radiates these the most. And that's why it's white hot. So this temperature, 5,000 Kelvin, at the very middle of the electromagnetic visible spectrum. So this and temperatures above that appear white hot because all of the colors are at high intensity. So that's kind of interesting. Things radiate. We can look at them and kind of get an idea how hot they are by what color they are. Because if the peak is, you can see at 4,000, the peak came more in the red. That's why it was red hot, then orange hot, then white hot. Because as you increase in temperature, 2,000 K, 3,000 K, 4,000 K, the maximum, darn it, of where you radiate changes. So this curve here at 4,000 K, its peak is in a reddish color, and it would appear red. And then as things cool off, you can't see your eyes don't detect them anymore. You could still measure, you could have some instrumentation that would measure that spectrum, and you could see where the peak was on an instrument, but your eyes can't see them. You may wonder, people say space is empty and cold. The temperature of empty space out there in the universe, does anybody know what that is? Somebody throw it into the chat if you know about what the temperature of the universe, the empty space in the universe is. Anybody? Nothing? It's 2 or 3 Kelvin. It is very cold, near absolute zero. So the background radiation of space being a perfect radiator, the universe being a perfect radiator, all the frequencies are there. The peak is at 3 Kelvin, all the way down there. The peak is at 3 Kelvin. And you're at the wavelength is in the microwave region. So you go all the way from the visible through the IR out to the microwave region. And that's where the peak, so when you measure all the radiation coming from space, there's a peak in the microwave region. And that's why we say space is 3 degrees Kelvin. So that's kind of cool. You might have heard that term, microwave background radiation of the universe. That tells us the universe is 3 degrees in general in empty space. So this is just for fun. When you go to the hardware store, I'm always talking about the hardware store. I love the hardware store. You don't know me very well. I'm a mechanical guy. I like to build things, and even in my graduate career, I like to build I'm a physical chemist, so I like to build the spectrometer that measures those frequencies and tells us about molecules. I like to build the components. But when you go to the hardware store, you can buy LED lights now, and they are perfect radiators. They're very good radiators. And if you look at the package, they give you a color temperature. And now you have kind of an idea why that is. Because color is associated with temperature. So if you have color temperature low here, 2,700 Kelvin, that's warm and reddish. Not it's just pleasant, warm light. When you get to higher temperatures, this is 5,000 K, we saw that's bright white light where you're seeing many of the colors in the electromagnetic spectrum. So this gives you this bright light. It's very white. It's kind of harsh. This is at 2700 Kelvin is in the yellowish, the pleasant part of the spectrum. So these are nice in your living room, and these are nice maybe in your workshop, or where you sometimes in the bathroom where you want to see all the colors if you're getting dressed in the morning. So that's kind of cool. One thing that you might be confused of, the color temperatures you understand. The trouble is the way they name them is the reverse. They call 2700 warm white, and they call 5000 cool white. Darn it. And that's because artists named the colors first and not the scientists. So we went the artists, but they do put the temperature on there. So that is the color temperature, and we as scientists understand that that is hotter than this one, even though an artist would tell you that's a cool color and this is a warm color. So light can be absorbed and emitted. We've already kind of we're already alluding to this. When the light comes in, part of what's happening in your eyes is an absorption of the light. So when light encounters matter, it can be reflected away, but it can also be absorbed, or it can pass right through. And many of those very high wavelengths pass right through. We know X-rays pass right through, and they get stuck on the bones and the hard stuff. And that's why we can take X-rays, because the light, all the X-rays get through, except the ones that run into bones. So the bones look different on the X-ray film than the soft tissue. So absorption and light can also be emitted. Those perfect radiators were emitting radiation at all frequencies. Many things are not perfect radiators. Some just emit at specific frequencies. And there's different flavors. We're going to talk about this more, but you can have continuous kind of absorption or emission. So I've drawn a curve here, and this is saying this is the peak. We absorb most of our color here in this green-yellow region. And here's a different substance where it's absorbing more in the blue-green and in the red, violet, or red down at the end there. So absorption, you can absorb bands. When we call band a collection of frequencies, a set of frequencies, or you can actually absorb just one frequency. We call that discrete or line spectrum. Discrete means, whenever I say discrete, I mean one in this class. So you can absorb a specific frequency. And if you absorbed it from the spectrum, then to an observer, it will have disappeared. So if you're an absorber, a discrete absorber, light's coming here, it's got all the frequencies. On this side, I see light that's minus those frequencies because this stuff in the middle absorbed them. And it's often done, here's a substance, the hand sanitizer. This isn't absorbing any of the light because all the white light is coming through. This looks completely clear and white to me. And you could also emit specific frequencies. So there's absorption, or you could emit them. You could emit a broad range of frequencies, or you could emit specific frequencies in the electromagnetic spectrum. And this are going to be really important to us because these kind of emissions tell us something about what the molecules, the electrons in particular, in the molecules and atoms are doing. And the study of these is called spectroscopy. You look at the spectrum. So these are spectra emitted by, absorbed or emitted by atoms and molecules. We can actually see it happen in a demonstration here. This one isn't that interesting. Let's look at the other one. Oops, I shouldn't have closed Chrome altogether. Let's look at this one. This isn't more interesting because I'm in it. It's just more interesting. So here I have two colored solutions, and this one is red. That means the white light coming from here is almost all absorbed except the red, because the red comes through to here. Same thing, this blue. The white light comes through here, but I see blue. That's actually a spectroscopy experiment. The light comes in, some of it is absorbed, and we can tell that that happened. So I have a pen laser here. It's red, and I'm going to say, take that pen laser. We're saying red is not absorbed by this solution. It should pass right through. So we're going to take the pen laser and bring it close to my hand again through that red solution. So you can see it going right through the solution and still hitting my hand. And we expect that. Red is not absorbed by that. It passes through. So this solution, which is blue, we're thinking must be absorbing the red, because the red isn't getting to our eyes. We're the detector. So here's the red laser. And as I bring it to the solution, boing, stops at the glass. It's being absorbed by the blue, doesn't make it through to my hand. So that's a very simple absorption experiment. But interestingly, we said you can have emissions of discrete lines, individual lines. So here's Lonnie in the demo lab, and he has a lamp here, a mercury vapor lamp. And white light, as far as we're concerned, it looks like white light coming out of it. But if you send it through this instrument here, this grating, it spreads out all the frequencies that are coming out, and it gives you the spectrum on the screen. So this is what we call a spectrum, and this is a discrete spectrum. You got mercury, it's atomic mercury being excited. It's a light bulb, mercury light bulb. It looks like white light to us because we're seeing all these wavelengths together. But this instrument, this grating here, separates them so we can see the individual lines. So that's just like the picture I drew. In fact, how do I do it? Let's grab that. And let's look a little more closely at that spectrum. I don't see why this thing is always there. I tried to erase it 1,000 times. So here is the spectrum that Lonnie had. And we can see an orange wavelength, a green wavelength, a blue wavelength. And what he's projecting it on is a fluorescent screen. So the light is hitting, and there's not just reflection, there's fluorescence. The atoms in the screen are excited and they are emitting. So we see that's visible, that's visible. This one, this blue, is making the screen emit in a different color. So this high energy, and we know bluer is higher energy photons, are making the screen emit. So low energy to high energy wavelengths. And look at this. This is cool. Why is that line there? Well, this is blue. there's another line here in the ultraviolet. We can't see it, but the screen can. It's exciting the screen, and the screen is emitting light. How cool is that? Science. Excellent. So let's go back to our presentation here. So everything we know about atoms and molecules, you know you can't see them, atoms and molecules. Everything we know comes from radiation hitting them, some of it being absorbed or emitted, us detecting that radiation, and then deducing stuff about the molecule from what it radiates and emits. It's called spectroscopy. That's what I do. I'm a spectroscopist, a physical chemist. There's two kinds of chemists. There's physical chemists and there's cooks. The people who mix the chemicals together and make stuff, the organic chemists, all those guys. And then there's the physical chemists, and we tell the people who are cooks what they made because you can't see the molecules. So, and it's hilarious. If you ever, okay, modern television, modern media, if you are watching something where there's a laboratory scene, it always looks the same. There are lab coats, there are safety glasses, and on the bench, there's a microscope, invariably. And somebody will go up to the microscope and say something like about a molecule, like a DNA molecule. Oh, their molecules are mutating. No, there's no optical microscope powerful enough to resolve atoms and molecules. And you might know why that is. The wavelengths of the visible light are too long to see them. The energies interact with but the wavelengths can't resolve them. The amount of resolution you can get depends to an extent on the wavelengths that you can refract by your lens. So there are no molecular microscopes. That's a lot of hooey that we're fed from the popular media. I wish they would just consult me. They must have, right? They must have scientific consultants. Why does that stuff get through? Star Trek, littered, of course, with problems. They're much better than the old days. But Star Trek: The Next Generation. Have you anybody seen that? I can't tell. Thumbs up. But there's this character, Geordi, and he wears this visor. For some reason, in the faraway future, you can't fix eye problems. I'm not sure why, but he's got this visor, and he's always saying stuff like, "My visor is sensitive to the entire electromagnetic spectrum." So apparently, he can see the wavelengths that we can't because he's got this visor on. So one episode, Geordi and the doctor are trapped in this bay for some reason, and Geordi's an engineer, so he's taking panels off the wall and trying to get into the circuits to open the door. And the doctor, who's useless usually, is sitting next to him and puts her hand on the wall, and she goes, "Whoa, that's hot." And Geordi looks over and goes, "Where?" "Entire electromagnetic spectrum." He should have seen the infrared radiation and said, "Look out, it's hot over there, doctor." I'm the only one who notices that stuff. Anyway, what color is an object with the absorption spectrum shown? So we're absorbing this light. That's the maximum of the absorbance. Let's just talk through this one together. So if I'm absorbing here, the maximum absorbance is in this red region. So those are the regions that aren't passing through. These are the regions of the spectrum that do pass through. So this object with that spectrum would appear blue to us because the blue passes through. That's we just saw that example. I put the red laser and it didn't make it through the blue solution, but the blue does. Let's look at this one. So glass is transparent. So what's the absorption spectrum of glass? Now, this is a broad absorption spectrum going from lower than the ultraviolet to longer than the infrared. What do you think is the absorption spectrum of glass? So let's think about that for a second. I'll start the thing because it's in the middle of the galldarn board, and we'll take a vote. Did I do that wrong? Oh, thanks. Okay, guys, we'll come back together and see what you're thinking. Oh my, right across the board, pretty much equal for all of them. So I guess you need my thinking on this. What we need, glass we said was transparent. We said the visible region kind of spans between the ultraviolet and the infrared. So there's visible wavelengths all in here. So that means visible wavelength, the colored wavelengths are here. This substance with absorption spectrum 1 doesn't absorb any of the visible. And this one absorbs some of it. And this one absorbs all of it. So the only one we can be sure is absolutely transparent, absolutely clear, is the one that doesn't absorb anything, transmits all the visible light. So number one is the one that's going to be perfectly transparent. What do you think number two is going to be? It absorbs the blues. I mean, this is hand wavy, but if this is actually correct, it's absorbing the blues and greens, and the reds are passing through. So this one is going to have some color depending on where that actually falls. And this one, that's kind of an interesting one. Number three, substance number three, what color is that? Or what does that look like? So we went from transparent to red to black. All visible light being absorbed by that one. Okay, let's talk about a very, very interesting subject. So we've told you light is a wave, but we've also told you that we can't resolve the wavelengths. We don't see them even when they're macroscopic. The radio waves, even when they're macroscopic, we can't resolve them. How do we know that it's a wave? Well, waves do particular things. And water waves do particular things, and it's absolutely analogous. Waves on a pond, absolutely analogous to light waves. All wave phenomena, the reason we stopped and talked about properties of waves, all wave phenomena behave the same. So if you're a wave, you have certain characteristics, and I can tell you're a wave by doing certain experiments. So the experiment we do to detect a wave is called an interference, diffraction and interference patterns. You pass light. Here, if you pass light through a hole, so here's some green light, it's passing through a hole, it spreads out, it diffracts. So that spreading out is diffraction. It's very intense here in the middle, and then it gets lesser intense on the side. And you know that if you take a pie plate, you poke a hole in it, put a flashlight on it, the far away, the image of the hole is bigger and dimmer because the light diffracts. Okay, this is just a single wavelength doing that. With your flashlight, it's all wavelengths in the visible region. So you get this intensity spectrum here. Okay, it's intense in the middle and weak at the edges. So the intensity is, we're going to make this analogy a lot. So wave phenomena, the intensity, we're going to correlate with probability of the light hitting there. So it's more probable that the light hits there. So that's a high amplitude, high intensity, high probability. If you have another slit, same thing. There's the B slit. If you open both slits, what you might expect is this. A bright spot here and a bright spot there. So these high intensity, these are bright spots. You wouldn't see a hill if you were looking at this screen. You'd see a bright spot here and a bright spot there, getting dimmer as you go away from them. And if you use your flashlight, that's what you would see with your two holes. But if you use light of a single wavelength, so green wavelength here, and you get your slits oriented just right, width and spacing, what you see is a pattern of bright and dim spots on the screen. Bright, dim, bright, dim, bright, dim on the screen. And I'm telling you that is a property of waves. So if a wave phenomena passing through would do that, and we kind of know why already. if your waves, and you have now waves traveling through this slit and waves traveling through this slit, we know that they can add and subtract. We saw that when a peak and a peak came together, we got constructive interference and we got higher amplitude and intensity. But when a peak and a trough came together, we got destructive interference and we got low intensity. That's what's happening here. You have light waves coming from this slit and light waves coming from this slit. And when they both hit here, they both traveled exactly the same distance. So they added constructively. They were in phase. They traveled the same distance. Two peaks overlapped. When light beams from here hit here at this one had to travel farther than this one. So by the time they got to here, this one was peaking and this one was troughing. And I got a dark spot there. So this phenomena tells us light is a wave. Lonnie can do it for us. He shines a red laser through slits and you get spots. I won't show you that demo. It's not particularly interesting. This shows you all that same information. So now you have a very interesting probability distribution of where the light is likely to hit. Very likely to hit here, less likely here, kind of likely there. This overall envelope, so there's the overall envelope, that's the diffraction envelope. That's the one you see with the single slit. And the spots, so they're getting dimmer because of the diffraction envelope. And they are bright, dark, bright, dark, bright, dark because of the waves. So let me ask you this. How will the two-slit interference pattern change if I increase the wavelength? So this one is for this green light. I'm going to increase the wavelength. What happens to the interference pattern on the screen? Think about that for a second. We'll take a vote. Okay, if you haven't pushed a button, go ahead and do that. Okay, let's see what you're thinking. Many of us are thinking C, and a couple A, and not very many B. B has kind of stayed the same. So I think you had, I think I agree with you. It's going to change when I change the wavelength. How is it going to change is the issue. So let's talk through it together. I think I have some pictures. So we talked about the slits. There were equal path lengths here. So that got me a bright spot because the waves have to travel the same distance. So they're both up when I hit here. To get to the next bright spot, I have to go, this has to be at least 1/2 wavelength farther. It has to get to another high to get a bright spot again. So this distance up the screen must make this distance half that wavelength, at least half a wavelength farther to get to a bright spot again. And we were saying that reds are longer wavelengths than green. So a larger lambda gives you a greater spacing, and that's C. Fantastic. We understand waves going through slits. That happens for water waves. I have a demo there to kind of show you water waves, but it's that bright white background again, so I'm not going to show it to you. I have a little device coming to my house today that hopefully will let us switch the live stream from this display to that camera and back and forth, and we'll be able to just do those demos beautifully for you. So I'm just going to talk through this one because you probably you shouldn't leave Chem 1, shouldn't leave any science class without knowing why the sky is blue. So let's just talk. Here we're going to scatter the light. There's going to be a medium like air, and the wavelengths are going to get scattered around. So it's tightly collimated beams, you could say, but then as you go through this medium, it gets scattered, and some wavelengths get scattered more than others, more disturbed by the medium. And here you can see blue is highly scattered, and the oranges are not so highly scattered. So if you look at the light, so I'm standing here, I have a light source, I have this medium that scatters it, the light coming through here, and the light over here perpendicular. This would be the highly scattered light. And this would be the light that's not so scattered, maybe the rest of it. And this curve is quite steep. So the scattered light is mainly in the blue, and most of the rest goes through. So that's why the sky is blue. If you look right at the sun, please don't do that. But if you don't be the president of the United States, directly around the sun, directly where the light is coming from us, where it's this situation, the light source getting right to us, the full spectrum, almost all the spectrum, all the colors. So it looks like white light. If we look anywhere else in the sky, we're seeing mostly the scattered light. So the scattered light gets to us because it's being scattered around through the atmosphere. And that's the light that randomly gets to us, scattered out through the atmosphere. We look at it and it bombards us here. So that's why the sky is blue. That's why it's why sunsets are red. So when the sun is near the horizon, then you have the longest path length really of light to pass through. So you get very good scattering. The blues are very well scattered out, and you see the light very well that's not scattered, the reds. And the more particles in the atmosphere, the redder it gets, the better the scattering is. So, on smoggy days or fire days, we had a lot of those, sunsets are very red. Woohoo, take home lessons. Now you're glad you came to Chem 1 today. So here's just the answers to those chem quizzes. The difference between the scattered and the low scattering is there. So that's all we were going to say about that. So let's continue talking about the intensity of light. So here, I'll talk through this one with you as well. Here we're talking about the intensity again, being absorbed, but broad wavelengths being absorbed, lots of it. So here's a high intensity reddish light going through some kind of medium and diminishing in intensity. So this is the red laser going through some blue medium and diminishing. The light is bright enough that some of it penetrates, even though this substance is trying to absorb it. So it's bright enough that some gets through, but some fraction, half of it, is absorbed. If you put two columns, two blue solutions in the way of your light, can you absorb the rest of it? Will it go to zero? Or will it go some other way? And I think you probably kind of know the answer to this. It's going to dim again, but it's going to dim by the same proportion. We're not going to absorb, just because we absorbed half of it, we don't absorb the other half. We absorb half the light coming in again. So half the light coming in is absorbed, and it gets a quarter of the original intensity. Okay, so that's the general absorption phenomena. So you can do this with light. So imagine you're doing it with, I got a flashlight here, but imagine you're doing it with monochromatic light, one wavelength, monochromatic. A laser is monochromatic. You're shining it, and you start to put those filters in, and you take half of it away, and then half again, and then half again, and half again. And it's getting dimmer and dimmer and dimmer and dimmer. Does that continuously go to zero? That is, does the dimness just stop and go to dark? It's like the atom experiment we talked about in the first. If you take aluminum and you cut it in half, and you cut it in half, and you cut it in half, keep cutting the sample in half, does the sample just disappear, or do you get these discrete atoms of aluminum at the end? Believe it or not, same thing here. You cut the light in half and half and half and half again, and what you see are flashes. Not zero, but flashes of light. And it's, you wouldn't think that at first. You'd say flashes, little bits of light, little packets of light. That's what happens. You can filter light down to tiny packets. So it seems continuous. You got all these wavelengths. It seems like there's no breaks in it. But if you filter it down, the intensity keeps dropping until it comes in flashes, packages of light. We call those packages photons. This really happens. It turns out your eyes are sensitive to about one photon. You don't have to use an instrument to do this. You could do this you have to have very good eyesight. You have to be a baby. You guys. Very dark room. You sit in a very dark room for a very long time. Let your pupils completely dilate. And then you let this light come into the room, and not any of the bright, all the filters in place. And you look at the origin of the light, and you can detect, if you have very good eyesight, you can detect the flashes. You can detect the graininess. Your eyes are sensitive to the graininess, the discrete nature of light. We call those discrete packages photons. So blink, photon, blink, photon. Here, there are billions of photons being carried along the waves. The waves are composed of billions of photons. All these little things add up, and that's why it's bright. Each one is adding its brightness to the group. So bright light, high intensity, high amplitude is many photons per second. That's the energy carried in the wave per second. It's the power of the wave. The photon energy is defined by the frequency. So we've talked about that, but now it takes on this new meaning, because we said, well, the energy that is proportional to the frequency, but now we're talking about a discrete package of energy, a tiny flash of energy, a tiny bit of energy that has this magnitude. The frequency times a constant, Planck's constant, and it's a ridiculously small number, 10 to the minus 34. So these are ridiculously small, and the frequencies are ridiculously small. So it's a ridiculously tiny package of energy, very small package. That's why we don't resolve it, and it doesn't really affect our everyday existence. Tiny package of light comes out. We call it a photon, and that's its energy. So light has this particulate nature. And we've seen the electromagnetic spectrum, and now we can think about it again. These long wavelength, longer wavelength here, lower frequency means lower energy. Long wavelength, low frequency. Here, the visible, higher energy, and here, the getting into the ultraviolet, high frequency, high energy. All related by the speed. The intensity now, these are high intensity, a lot of photons. This is a bright light. High intensity, the intensity goes like the amplitude squared. So the brightness, we take the square of the intensity, approximately. So that we understand now, lots of photons per second, bright, high intensity, high amplitude, lower energy, fewer photons per second too, because it's not as bright, and lower energy for each individual photon. Here, high energy photons, high impact photons, not as many of them, not as bright, not as many of them per second. We know it's an electromagnetic wave, these guys. So that means along this wave, these oscillating electric fields, they would affect electrons. They could set electrons into motion, just like that duck on the pond. The wave comes in, and it's going to make this oscillating electric field makes that electron move. We said last time that's how your antenna on your radio detects the radio waves. The electrons in the antenna are moved by the radio waves. And you can actually make that electron move. You can give it the energy of the wave can be transferred to the electron and give that electron some kinetic energy. And you can, how much? This much per collision between the electron and the wave. The wave can give a photon's worth of energy or 2 photons worth of energy, however much is carried on the wave to the electron. And the electron takes it away as kinetic energy. So I'll just we'll just start here next time. We have office hours right now anyway, isn't this Thursday? So we'll take some office hour questions. Do it the same way we did last time. You can ask them directly in the Zoom. We'll bring you all into one Zoom, and I'll bring my screen around so I can hear you. And turn your camera on, say hi, and ask a question if you have one. You may not have any questions, but go ahead. And any questions, you can ask them in the live stream chat, anywhere you'd like. Go ahead. You can give it. I don't hear anybody speaking. Yeah, no, I think no one's going to say anything. We have one question from the live stream, so we'll take that. You guys get a question ready here in the Zoom. Go ahead, live stream.
If the light, I'm guessing this is from the diffraction and interference ChemQuiz question. So if the light coming through one of the slit went through extra distance right before entering the slit, could the peaks of wave be displaced relative to the other light and displace the pattern?
So the question is, a good question. The question is kind of this. We had the light waves coming in here, and we said a wave phenomena is coming here. Let me draw that a little more carefully. So let's draw it over here so we have some room. Here's our slits, and here's the wave phenomena coming at it. And the question is, if I go through this slit, we know that that takes what the distances are, and that's causing the waves to be out of phase. The question is, what if something was happening out here and they weren't really in phase to begin with? They didn't go through the slit in phase. Yeah, then all bets are off. Then you won't get a diffraction pattern. You'll get a mess. But what we do is we use what we call coherent light. Every wave in the light is exactly in phase. That's what lasers do. So they're exactly in phase when they hit here. In phase means same peaks and valleys, and that's why you get a diffraction pattern. Good question. I think that was what you were getting at. Questions from the Zoom? There's a bunch of you there. Anybody want to say anything? I hope it was right. Did I have the wrong? It was off by 1.7. 1.7 is close enough to 2. 3.7 wouldn't be. Was it 1.7? Negative 3.7? Oh crap. You guys all checked it and came up with 3.7? Well, 8.314. I did it. And I got 2-ish. Shoot. Okay, well, good point. If it's really far off, then let's throw that question out. I mean, -2 is the only thing anywhere near that, obviously, but still, if it's off by a factor of 2 almost, that's not fair. Okay, well, yeah, double check the calculation. Yes.
So Jocelyn said, okay, so she has 2 questions. I have a question. So from the ChemQuiz of the glass transparency, I thought it would be C because on the spectrum, IR is shown on the lower energy side.
The question is on that ChemQuiz where we were talking about the transparency of glass, is in here somewhere. So the question is, we have transparency of glass, and The question is, IR was shown. What's the question again?
It's, I guess she meant to say that IR should be. I think she just saw the horizontal axes and that like IR is higher energy, but like we know that IR is lower energy compared to UV.
Oh, we're not plotting energy. We're plotting wavelength. So short wavelength to long wavelength. This is a wavelength axis, not an energy axis. Yes, the frequency, the energy goes the other way. Other questions? Yes. Yes. And is my mic on? Oh, I'm coming through your. Yeah, mute yourself there because I'm coming right back out. Thanks. The question is, for that perfect radiator, that perfect emitter, is that also a perfect absorber? And the answer is, when you're doing those theoretical calculations and you're talking about these perfect things, yeah, we assume it's a perfect absorber and radiator. In fact, the term you'll see if you read in textbooks is black box. This is the black box experiment. It's a perfect absorber, so it absorbs every single wavelength and would appear black. So the absorbers and radiators. So you take your the reason I don't call it black box is because that makes the whole thing confusing. So the phenomena is the same. All I want you to think to understand is that things that do perfectly radiate have that phenomena. However, perfect radiation corresponds with, in general, if you're modeling this in any kind of experiment, perfect absorption, and it's called black box radiation when you're reading it in books. We're not going to have a lot of questions about you're not going to make calculations on that. That's just something we observed. It's an interesting phenomena. Color temperature was the thing to take away from that. You get at higher temperatures, the radiation peaks in those visible ranges. Does that kind of answer your question? Yeah, it's just terminology. I've always hated the term black box. I don't know why. I mean, you start reading about it in physics and you go, why are you calling that a black box and giving me this radiation spectrum? So you could call it a perfect absorption spectrum if you want, but then it's annoying because you're not seeing the colors. So other things? Sure, go ahead. Yeah, have and have. Yeah.
Right. So is that because the process is inherently probabilistic, as in it's relying on the probability that the photon will encounter?
Absolutely. There's a probabilistic aspect to it that comes from many factors of the absorber. So there's a certain probability when a photon is impingent on a particle. There's a certain probability that the interaction will occur. Absolutely. But if you have a macroscopic thing, then you have also the number of particles and you have the diffraction to think about. So it gets a little muddy. But if it were one particle and one photon, absolutely. Even if it hit the particle, there'd be some finite probability that it would be absorbed.
Okay. And then this term optical density that people use. I've heard this term used a lot. How, if at all, does this relate to like the density in the vast sense that we're used to? And is it in any way misnomer or?
No, that's very similar to what we're saying. That uh, i- in a sense, boy, that term is used rather loosely in a lot of fields.
Okay, so one should not take it very.
It's used so loosely that it's one of those things where people say spontaneous, and they could have a lot of different meanings. So um, uh, I'm trying to come up with a definition in terms of photons and probability. Uh, um,
So for instance, I know that like to block, let's say like to block X-rays, we use lead. And so I know lead is dense in the vast sense. But then also when I try to visualize like the probability of encountering an obstacle, I think, wait, but then like spacing density seems like the relevant thing. And so I'm trying to get to figure out like what are the factors.
oh, I see what you're saying. So yeah, so we're talking about the transmittability, the percent transmission through an object. So all those things are uh, absolutely related. So in that case, packing structure matters. So the mass density matters. If you're going to encounter photons, the number of particles you put in the way matters. So in that case, if you're going through the same path length, then the more dense you are, the more absorption you'll have. We can absolutely say that for sure. So mass density is related as long as your path lengths are the same. You encounter the same number of particles per meter along the path of the beam. So that's physical density.
Makes sense.
Other things from the gallery here? Okay. Great, guys. We'll see you Monday. Hear me. Sorry. Okay, the stream stopped. So now this mic, can you hear me through this microphone? Okay. Yeah, no, I can hang around. I was just, I kind of hang around until the questions kind of peter out. But yeah, I have time. Oh, okay. The stream is going too. Okay, go ahead. Yeah. Daniel, if you want to chat.
Yeah, so one thing that I've been wondering, this is very high level. One thing I've been wondering is I know that so many of these equilibria are dynamic equilibria, where I guess if you zoom out, it looks like an equilibrium just because of kind of the statistics of what's going on. But then when you zoom in, like things are changing like all the time. For example, at like the liquid gas interface, but it's just that it looks like
Yeah, like optical, yeah, like optical density. So you might be a little careless. So there's the issue of perfect balance or equilibrium. So the free body diagram, you're looking at the sums of all the vector components of all the forces involved, and you're looking for balances. If the particle is static, maybe you can balance. If it's moving, you can calculate the imbalance. So that so are there instances in chemistry like that? Is that the question? So is the point where there's like a tipping point, there's this perfect balance, and would we call that equilibrium?
So I'm like senior undergrad, and I have like taken material science, taking multiple things where we talk about equilibria. And are there any equilibria in chemistry to keep in mind that are not dynamic, like where it's truly that?
It's at that tipping point. It's on the knife's edge where everything is perfect and it's not dynamic.
Different things are like balancing out.
Nothing of particular interest. I mean, chemistry, we almost 99.8% of the time, the statistics matters because it's hard to deal with small numbers of particles. I'm trying to think of a spectroscopic analogy. So you can balance properties, but statistics almost always gets in the way. So for instance, yeah, we have this bulk property. That is the problem, and statistics always gets in the way there. There are properties of atoms and molecules that you would say, well, can I? There's a spinning or oscillating molecule. Can I stop it from spinning, like, and balance the forces so it stops spinning, like a macroscopic thing? And the answer there is no. You can't make it stop. There's the quantum mechanical aspects come in to play. So that tipping point doesn't exist. You can't as a particle moving through space, equal forces, you could get it to stop. Electrons, you can never do that to. There are particles that you can do that to, but you always do it in the bulk. In fact, next time we're going to talk about laser cooling. How do we, can you bring molecules to a stop, get to that tipping point by pushing them equally from both sides? And you can get very cold. You can get very close to stopped, but you can't get to that perfect balance. Tiny things, they're just dynamic in the quantum mechanical sense. The matter is dynamic. The matter is too spread out to get to a balance. An experiment. Okay.
Talking about the lowest, getting to that point of kind of lowest energy, and I guess that is thermodynamically preferable as time goes to infinity. I was thinking, so what if you have a landscape where there are little wells, and then you have this really deep well, but the deep well does not go to the lowest energy, as in
yeah, sure. Yeah, there's some traps along the way. That is literally the difference between kinetics and thermodynamics. It may be that kinetics limits you from ever getting to that deep well. The way drawn it there, that deep well is kind of a trap because there are other places on the landscape that are lower. So thermodynamically, you'd want to get all the way down that mountain, even though there's that trap in the middle. And so it just becomes a kinetic problem. Over time, how many particles in your distribution have enough energy to get out of your trap? And you can arrange it so none can ever get out of that trap. If that well is so deep, even though there's somewhere deeper down here, it's not accessible.
Oh, interesting. So I thought, okay. So I thought the thermodynamic kind of preference.
There's no when in thermodynamics. So it tells you this state may be lower, but inaccessible in a physical situation because of the kinetics. That's okay. It can be low but inaccessible. And that's what the picture you drew is. That's low, but it's not accessible to particles in this well because those particles can't get out of there. It's called local stability. So there's this local, yeah.
Okay. I think that what this led me, I think, was that in my some point in my education, I was told that as time goes to infinity, that that whatever specimen you're observing will reach the kind of thermodynamically preferred state. Is that wrong?
Yes. If you tell that to me, the trouble is time is not a thermodynamic variable. So you cannot say at time infinity. All you can say is what the favored state is. So I think you've just kind of, and I was doing that hand waving thing too. If you wait long enough, will it get there? Thermodynamics does not answer that at all. You have to go to kinetics to answer that question. So infinity, will it get there? It's not a thermodynamic question.
Right. I think the context in which that was explained to me was people were asking, so if it will never get there, like isn't it kind of fake or does it not matter? And I think that when pressed, whoever this person was, this instructor, when pressed, just said like imagine it as if time was going to infinity. But okay.
Yeah. Yes, yes, that's one of the things I think I alluded to. I was kind of having a similar conversation with a professor I had at Michigan State, and he said, Mr. Kubinec, time is not a thermodynamic variable. Just can't answer that question. You don't have the tools in thermodynamics to answer that question the way you phrased it.
Okay, got it. Sounds good. I will let Swathi or whoever else take this step.
Okay, what do you have something else, Wavi?
Yeah, sorry. That's actually what Daniel asked was thermodynamic when I was getting at. Like, at what point do you make the distinction between like thermodynamics and kinetics? Because when you talk about entropy, we do talk about like the arrow of time.
Yeah, no, I'm glad you brought that up because that is that the entropy is suggestive of time because it tells us where equilibria lie, and our experience is that if we have lots of energy to work with, then things will get out of those local minima and they will end up in the global minima if we have lots of energy to work with. So and entropy says, where will they end up? They'll end up in these free energy minima. And as they get there, energy is dispersed in this annoying way. So some of this heat, some of this, the particles are getting so disorganized that they cannot influence the other particles in the system. So you can have a warm system, but so much entropy that no particles can, that's what too many microstates are. You can't get any concerted work to happen because you're spread out over so many microstates. So many microstates are accessible that no one can come together in a compact set of microstates and do something. So that's the idea of entropy always increasing, and that just the fact that that happens over time is the question then becomes, if you're asking at that, what is time? The expansion of the universe, is that time? Because that forces entropy to increase because the volume just gets bigger. It would be nice if time as a parameter would emerge from a mathematical picture. So that might sound abstract, but when you're doing calculations about the universe, you put time in artificially. You say time is passing. There'd be nice if there were a mathematical calculation where time emerged, and you have this mathematical formula where time is a natural parameter of the universe rather than this parameter we always add to the system. That would be cool. But as far as I know, astrophysicists haven't gotten there. Well, actually, you can get there, but it's completely a mathematical abstraction. So you use what you call Euclidean, non-Euclidean geometries, and you build a universe that's non-Euclidean. And it turns out when you get to the 10 or more dimensions of this non-Euclidean space, then time emerges. That's not helpful for our three-dimensional physical space. No, not related.
Yeah, I guess that's like a super abstract question, but I think that's sort of what I want to ask.
Yeah, how time comes in, and is it fair to say there's a time direction of the universe? Yes, because it's our physical experience, and then we are muddling things, because all it's saying is eventually, and now I'm going to use a time parameter, if there's enough energy interactions in the universe, eventually what's going to be happening is all the particles will be as far away from each other as possible, and they'll all be spread out evenly in the universe. That's maximum entropy. So that is our fate, because we observe that the more thermodynamically favored states are the ones where that process is happening. The spreading of the particles is happening. So, and our experience is in time. We unfortunately live in time. So we see this preference to this increasing entropy. It's just a relentless spread of the particles. Once the particles can't influence each other anymore, you've reached maximum entropy. That's the point where you have the same energy you had in the Big Bang, but no one part of the universe can influence any other part of the universe, because it's all equally spread out.
Okay, so dark energy can still be accelerated.
Yeah, that throws a wrench in the works. Yes, you have all the energy that you started with. Your energy didn't go away. It's just so spread out. There's so many microstates that you are in that state and you can't get back. It's this irreversibility aspect. Once you go there, there's no going back. That forces you forward in what we call time. A spontaneous process is irreversible. The reverse does not happen on its own. You can add energy and make a reverse happen, but if you do that, you increase the entropy way more somewhere else. So there are processes, once that process happens, and it essentially for all natural processes are irreversible, entropy increases. So if it's a tiny part of the universe, I can say, oh, that happened and entropy increased, but I'm going to take some energy from over here and make it go back. But then over here, my entropy went up more than it decreased over here. So I always lose. And so this now is scattered. And this guy got, entropy went down over here. Entropy can go down locally. That's fine. It's just universe-wise, globally, it cannot.
What about the scenario in which the universe goes into the big freeze? So all kinetic energy becomes potential energy and things just kind of come to a standstill. Is that thermodynamically special, or is that just
The big freeze requires gravity to do something crazy. So space to do something crazy. That is space stop expanding. Mathematically, you can do it in both directions. I don't remember. I haven't looked at this in a long time. There is when you have the equations you're using it's not even equations. It's usually some kind of mathematical simulation to decide, will the universe expand indefinitely and we go to maximum entropy, or will we do the big freeze and come crashing back together? There's that tipping point. There's that astronomical constant. And it's been thoroughly measured now. And the tipping point is expansion. So we don't think the big freeze is going to happen. But I don't remember exactly what the whole details of that are. You have to ask an astrophysicist. Yeah. Yeah. Okay.